हेलो एवरीवन, वेलकम यू ऑल टू एआई की पाठशाला। एआई की पाठशाला आपकी अपनी पाठशाला है एंड आई एम योर इंस्ट्रक्टर अनु। एंड एज यू आर अवेयर, आई हैव स्टार्टेड अ brand new playlist called Statistics for AI and Data Science, and we have already covered 7 sessions in this playlist. Today is the 8th session, and today we are going to discuss sampling distribution and central limit theorem. So let's start. Let us understand what is sampling distribution. Once we understand what is sampling distribution, we will understand one of the most fundamental theorems and probably one of the most beautiful theorems in all of mathematics called central limit theorem. So let me write it. This is my central limit theorem. Fine. We will come to central limit theorem a little later, but first let us understand what is this sampling distribution. So I will try to explain this with the help of an example. Let us assume a random variable x. X is the distribution of, this x is a distribution of income of all the people in the world. Distribution of incomes of all the people in the world. Fine. Here x is the population, not sample. So let me plot this distribution first. This is my distribution. So I am plotting one distribution. Fine. This is a population distribution. So this is a population distribution and it looks like this. Note, this distribution which you are seeing right now is not a Gaussian distribution. So let me write it as well. So the distribution that you are seeing right now is not necessarily Gaussian, Gaussian. Fine. Why this is not Gaussian? Because if you look at this distribution, this part is not symmetric with this part. This right hand tail is much longer than this left hand side tail. So it could be any distribution, not necessarily Gaussian distribution. So let us assume this x follows some distribution. It could be a Gaussian distribution, but it need not be. So x is the distribution of income of all the people in the world. And you will notice that there are a very small percentage of people who will make a lot of money as per my distribution. Now, what if I take random sample from this entire population? If you recall, when we started statistics playlist, we learned what is the difference between population versus sample. Fine. And we know that sample is basically a subset of my population. So if this is my, let's say, population, then let's say this is my sample. Inside this population, this is my sample. So we know these things, I suppose. So from this entire population, let us assume I pick up a random sample, and that sample size, let's say I'm taking this sample size as n. So this is my sample size. And let's say just for simplicity, I'm taking the value of n is equal to 30 here. So n could be any integer. So I take a random sample of size small n. Let me call that random sample. Let's call this random sample that I'm taking, I'm calling this random sample S1. So this is the random sample, and I'm calling this of size n is equal to 30. And let's say this is S1. I am calling this sample S1. So what I am doing here is, from all the people who have some income in this world, I am picking up randomly 30 people. That's why n is equal to 30. We will understand why I am taking n is equal to 30. N could be 10 or even 100 or even 1000 or even a million. So I am picking up 30 people from this distribution X and I am putting them in a set S1. This is my first sample. Similarly, I will again sample 30 random sample of size n is equal to 30 and I will create another sample, or I will create another set and I am naming it as set S2. And remember one thing, these two samples, this S1 and S2, which I have taken from the population X, these two samples were picked up independently, which means I pick up this second sample independent of my first sample. So now let's assume I keep doing this. That is, I keep sampling the size of n is equal to 30 from my population. So let's assume I have done m such sampling. Fine. I have done m such sampling, m random sampling of size n is equal to 30. I have done so. So this is like I am putting it Sn. This is first, this is second, and this is my m. Let's assume I have done this m sampling S1, S2, S3 till Sm. So whenever I sample from the population, I get a set of S1, S2, S3, S4, so on so forth till Sm. Let us assume that I want to compute the mean of all these samples, that is from S1 to Sn, whatever sample I have created, I want to compute the mean of all these sample incomes. Let's suppose the mean of the first sample is x1 bar. This is the mean of my first sample. The mean of my second sample is, let's say, x2 bar. The mean of my Sm sample is xm bar. And remember, this is a sample mean, not the population mean, because from this population X, I have first created my sample. Thereafter, I am calculating the mean of these samples. Fine. So these x1 bar, x2 bar till xm bar is the mean sample, not the population sample. And all these samples have a fixed size of 30 because n is equal to 30 I am taking. So all these samples are basic sample mean. Fine. Now comes the interesting part. Now I have x1 bar. So this is my x1 bar, x2 bar, this is my x2 bar, this is my x3 bar, so on and till xm bar, and this is my xm bar. Fine. So we have m sample means, x1 bar, x2 bar, x3 bar till xm bar. So what we have here m sample mean. Got it? Now one thing to understand, right now these m samples, 1 to m samples, have a distribution, because given a bunch of numbers I can compute a distribution, because I can compute a PDF for that matter. That's what I mean when I mean a distribution. Fine. So these xi bars have a distribution. These xi bar have a distribution, which is the distribution of sample means. So what I can say, I can write it here as these xi bar have a distribution, which is called the distribution of sample means. Sample mean. So we can also write it as distribution of xi bar. We can write it as distribution of xi bar is equal to sampling distribution of distribution of sample means of sample mean. Fine. So what is this distribution? It's a distribution of sample mean. And how did we get this sample mean? From this population distribution X, we sampled and we computed the mean of it. Fine. X1 bar, X2 bar, Xm bar till Xm bar. So the distribution of Xi bar is called sampling distribution of sample mean. So by far you might have guessed why I have explained you all this, so as to set the stage for central limit theorem. Now let's understand the central limit theorem, which is very fundamental and probably one of the most beautiful ideas in whole of statistics and mathematics. The central limit theorem states that when you take a large enough sample size from any population with any distribution, the sample mean, that is xi bar, will be approximately normally distributed, that is a bell shape, with a sample mean of mu, and the variance of the sampling distribution of the sample mean will be equal to the population variance, that is sigma square by n, that is divided by the sample size. This means that as the size of the sample increases, the variability, that is the spread of the sample mean, decreases. This variability, that is this spread, will decreases. So let me explain you this with an example. So let's understand. Let's assume x is a random variable. This x is a random variable with finite mean, F-I-N-I-T-E, finite mean and variance, sigma square. And let's assume I start sampling from x with a sample size of, let's say, sample size is equal to small n. Let's assume I created these samples. So I have created S1, S2, S3, so on till Sn. Now for each of these samples, let's say I can compute the sample average or the sample mean. So let us say I compute x1 bar for this sample, x2 bar for this sample, x3 bar for this sample, so on, so forth till xm bar for my last sample. This I am creating for all my samples. These are my samples and these are sample mean. Now comes the best part. Now I can say that these samples have a distribution which is xi bar. So what is the distribution of this xi bar? The distribution of xi bar is called the sampling distribution of sample mean. So what I can say here, I can write it as the distribution of xi bar is equal to sampling distribution of sample mean What central limit theorem says, xi bar is distributed with a Gaussian distribution, that is a bell-shaped curve with a mean of mu and a variance of sigma square divided by n, as n tends to infinity. So now let me break it up for you. This is very, very important and this is super beautiful. What I have written the theorem here. So let me repeat it. If x is a random variable with finite mean and variance of sigma squared, and if I take a sample of size small n, here this is my small n. If each of my samples is S1, S2, S3 till Sm samples I have taken, and if I compute the sample mean of each one of these samples, so the mean of my first sample is x1 bar, second sample mean is x2 bar, third sample mean is x3 bar, so on and so forth till the mean of Sn sample is xm bar. So I have computed the mean of all my samples. So there is a distribution for this xi bar, which is nothing but the sampling distribution of sample mean. What central limit theorem says is that this xi bar will have a Gaussian distribution with the mean mu. This is the mean. This mean is same as this mean. That is, this mean is same as my population mean. This is my population mean. So this sample mean is same as my population mean mu, which means this xi bar distribution will have a Gaussian distribution with the same mean as the population mean. And the variance of this xi bar will be sigma squared by small. Here is your n, this is my n, that is my sample size. So this n comes here in the denominator part of sigma square as this n tends to infinity. I suppose the theorem part is clear, right? So what it literally means is, if I have any distribution x, and let us assume this x is the income of all the people in the world, and this has a mean of mu and a variance of sigma square. So this could be any distribution. It's not necessarily a Gaussian distribution. So what I can write here, need not be Gaussian. Fine. This is very, very important. I have written it here clearly, need not be Gaussian. Every distribution has a mean and a variance. Sometimes not defined, sometimes infinite, but x need not be a Gaussian. That is very, very important and critical. Suppose I have sampled S1, S2, S3 till, let's say, Sm of sample size is equal to n. And let's assume n to be equal to 30. So I am assuming here that my n is equal to. So these are the sample income of all the income earning people in the world. These are the sample of 30 people because I am taking n is equal to 30. Let's assume m is equal to 1000. Fine. Which means I just needed to compute 1000 into 30. So because I just needed to compute 1000 into 30. This 1000 is my m and this is my n. So if I multiply this, this should be mn and this is like 30k. Which means I just needed to compute this 30,000 people's income. This is n, right? So I collected 30,000 samples, or you can say 30,000 observations. So I computed thousands of samples of size 30, which means I have literally taken data of only 30,000 people. If I compute the mean of these samples, I will get, let's say, x1 bar, x2 bar, x3 bar, so on and so forth till xm bar. Again, these are the mean incomes in each sample, and I have 1000 such samples because m is equal to 1000. Fine. If I plot the distribution of this with a mean, so if I plot the distribution of this I will get a Gaussian distribution. Gaussian distribution with a mean. This is the mean. So if I take the mean of xi bar, this mean is roughly equal to the population mean, which is my mu. I can estimate my population mean by taking the mean of xi's. This will be the mu, and the variance of variance variance of xi bar, which I can compute from the data, will be equal to sigma square by n. So if you recall, the theoretical part says this is true as n tends to infinity. But in the real world, if your n is greater than equal to 30, this n should be greater than equal to 30. Again, this is a rule of thumb. This is a rule of thumb that statisticians have come up with. So if n is greater than equal to 30, this distribution is called a Gaussian distribution, which means by just looking at this 30,000 data points, I am able to estimate the whole population mean and population variance. It means to understand the population mean and population variance of any distribution, I just need to know that they are finite and they are well defined. I can estimate the mean and variance of population by doing this simple sampling exercise and getting the sampling distribution of sample means. So central limit theorem says that the sampling distribution of sampling means for any population with a finite mean and a finite variance is a Gaussian distribution with mean tending towards the population mean and the variance equal to sigma square by n as n tends to infinity. But as soon as you have n that is greater than equal to 30, these things will start falling into place. So for any given random variable, you can estimate its mean variance by using the sampling distribution of sampling means very easily. This is why it is so powerful. The distribution could be from anything, that is anything in the universe. Any distribution it will take care of. That's why central limit theorem is such a fundamental idea in probability and statistics. Central limit theorem is significant because it allows statisticians to make inferences about inferences about population parameters to make inferences about population parameters even when the underlying distribution is not normal, provided the sample size is large enough. Sample size large enough. Fine. So in central limit theorem, we have talked about finite mean. So one question that might have occurred in your mind is, when do we have infinite mean? Fine. This is the question. Or is it possible for us to have infinite mean and variance? The answer is yes. There are some distributions out there which have infinite mean and variance, like Pareto distribution, Pareto, Pareto distribution. So this distribution has infinite mean and it's not defined in some cases. So there will be distributions which have infinite mean and variance. For those distributions, central limit theorem will not work. For those distributions, CLT, that is central limit theorem, will not work. Will not work. This is very important. There are extensions to central limit theorem that work, and there are many forms of central limit theorem because it's such a fundamental theorem that there are many ways of writing central limit theorem. So there are a lot of extensions even to distributions which have their extensions. So it is a very fundamental area of research even today. I will discuss the Pareto distribution in a separate session. So this is all for the day. If I really added any value to your learning, consider subscribing to AI Pathshala and keep asking your doubts and putting suggestions in the comment. Thanks for watching. Keep learning, keep smiling. See you in the next session.